So guess what we're starting today? The second law of thermodynamics. And this is a cool one. Some parts of it aren't that cool, but the parts involving entropy are. And this is going to give us two new, I guess, abilities, things we haven't been able to do with the previous approaches. The first one is calculating the efficiency of cycles. And the second one is, it's funny that we haven't been able to do this. Maybe you haven't thought about it this way with conservation of energy before, but this gives us the ability to calculate the direction of processes.
Because we've just been given it.
Yeah, so
I suppose it wouldn't matter either way, right?
well, so like if you think of like a simple conservation of energy problem, like somebody on skis without friction skiing down a hill, you know, and you go through conservation of energy and calculate their speed at the bottom of the hill. But we don't actually, we're just told they start at the top and finish at the bottom. There's nothing about it that says that. And actually, we could use the exact same equations to say, what if they're going this fast at the bottom? How far up the hill can they get, you know? So there's nothing to specify this happens first and this happens second. The second law of thermodynamics is going to give us that ability. With the ski thing, it really doesn't matter. It's the same equations. Well, it turns out that if you could use conservation of energy to say, okay, you know that, so say you take a hot lump of metal and you put it in some cold water, okay? And you can calculate what the equilibrium temperature of the metal and the water are going to be. But nothing we've talked about so far says that it starts with them at different temperatures and ends with them at the same temperature. Intuitively, we know that's the case, you know, but as far as conservation of energy is concerned, the first law of thermodynamics, it's just as possible for you to put these things at different temperatures together and for them to separate, okay, you know, into a hot thing and a cold thing, even though we know that can't happen. Well, the reason that it doesn't happen is the second law of thermodynamics. Okay. There are three equivalent statements of this law. So there are three equivalent statements of the second law. The first one is the most intuitive, and it really, we're not going to use it exactly, but you can show, and it's not too complicated, but I'm not going to go through it, how this is equivalent to the other two. But this first one is called the Clausius statement of the second law. And this one says that heat, remember heat is energy, it's a change in energy due to a temperature difference. And this says that heat only moves spontaneously from a high to a low temperature. Okay, so this is totally intuitive. I mean, if you put your hand against a cold window, the reason it feels cold to you is because energy is leaving your hand going towards the window, you know? If this Clausius statement wasn't true, you could sometimes put your hand on a cold window and it would feel hot because energy was going from the window to your hand and the window was getting colder. Okay, so this is totally intuitive, totally makes sense. You would have been able to make this statement yourself, so I don't know why Clausius is so great, you know? But this is, the only reason I bring this up is kind of to ground you to the other ones. This is all the other ones are saying. They've just figured out some cool, different mathematical ways to approach it that end up being super useful. But this is the one that we have, this is the intuitive one.
Clausius, a physicist? No.
I think he's the guy who brings us Christmas presents, isn't he?
Romans said that.
Santa Clausius, the Santa Clausius statement. But now we'll get to the two that actually have mathematical uses for us. The second one is the Kelvin-Planck statement. Planck. And this one says, okay, so this goes, there's a big jump in the complexity of what this is saying compared to the first one. But for a system that's in thermal contact with just one thermal reservoir, the work produced by the system over any cycle is less than or equal to 0. Okay, so let's think about what this means. So a thermal reservoir, you can think of that as like, you can think of that as a giant ice bath that's keeping something at a low temperature, or you can think of it as a boiler that's with a fire burning that's sort of an endless supply of energy as long as the thing stays below that temperature. So for the purpose of this, let's think about this thermal reservoir as being a boiler, okay? Like a fire, And what does it mean for W for the cycle to be less than or equal to 0? So think about the sign convention of W. So if the system is able to do work on the surroundings, then that would be positive. So what this is saying is, if all you have in your power cycle, in your in your power plant or whatever, your engine is a hot engine, all you're doing is shoveling coal into it, you can never get that to be a cycle and still do work, okay? You can never get it to return back to its starting state and still be outputting work. You can get it to return to its starting state, but then you have to do work on it, okay? So,
so is that basically saying the efficiency can only ever be 100% maximum?
This is
that
yeah.
sort of a statement saying you can't have like perpetual motion? Or
it's a little stronger than that. It's actually saying, so here's how to think of this. You can't have all the heat from a power cycle go into work, go into producing work. some has to be lost in exhaust. So how does it say that? Well, this exhaust is, think of this as a necessary second thermal reservoir.
Because heat is always being lost to the surroundings.
That's not, it's actually saying even if you have like perfect efficiency, you can't run a power cycle without using a cold reservoir to sort of like attract the heat flow is basically what it's doing, you know. You can't just pump energy into this system through heat and have it all produce work with perfect efficiency. You have to get that heat moving in a certain direction by also having a cold thermal reservoir. Okay, and what are we going to use this for? So the benefit of this statement is we're going to use it to derive what's called the Clausius inequality. Okay, so this is a pain, kind of, but if you had to think like which one of these statements of the second law of thermodynamics you're going to derive the Clausius inequality from, you would certainly think it was going to be the Clausius statement, but it's not. So just be aware of that. The Clausius inequality and the Clausius statement are totally different things.
It follows with thermo logic.
Yeah. And then we're also going to use this to derive the entropy statement. Well, the definition of entropy and the entropy statement of the second law. And then the third one of these is the entropy statement. And that says that for a closed system, meaning, so a closed system means no energy flow. That's you. Across the system boundary. The change in entropy is greater than or equal to 0. Or another way to think of that is the universe is a closed system. So if you think of all the changes in entropy in the universe, entropy is always increasing, you know. And so a lot of what we're going to be doing in this section is just making sense out of what entropy is, connecting the math of the mathematical definition of entropy to kind of intuitive ideas and stuff like that.
And then just a little clarification on 2. So we have this heat pumping into a system, but we have to tell it where to go by directing it and not directing it like we're using some of it.
Right. I think that's a reasonable way to think about it. Yeah.
But like that just happens now.
Or, I mean, another thing, say that again?
But that just kind of happens naturally like when you have a system.
Yeah, I mean, we'll see. It's easy to figure out how to use a cold reservoir to make this happen.
Right.
It's not like super tricky or anything, but yeah, the key is that you have to have both the hot and the cold reservoirs in order to harness this energy.
And it has to be a reservoir of fluid? Or...
No, there are different ways you can have. It's really just a reservoir. Just means it's something that, like, so if you're transferring energy from a high temperature reservoir to your system, or transferring energy from your system to a low temperature reservoir, the key thing that makes it a reservoir is it's big enough that the temperature doesn't change noticeably from that.
Okay.
So you're not watching those two things change temperature, you know. So that's like a boiler. You just keep shoveling coal in or whatever. They don't really use coal much anymore, but I'm just picturing the guy in the train. But they just keep shoveling coal in there and the temperature stays the same, even though it's constantly pouring out energy into the train.
In that case, the reservoir would be the atmosphere.
The cold reservoir?
Yeah.
Yeah, that's right. Okay, so we got these three statements. The Clausius statement is just kind of to ground yourself on. I mean, it's just, remember that even though it seems simple and the other ones seem complicated, they're saying the same things, and that's mathematically provable. But we're going to jump right into starting with the Kelvin-Planck statement. And this is the one, you know, we were just talking about it. You can't, bless you. Another way to think of it is you can't use all the heat that you put into a system to produce work. So you might think like, okay, the maximum efficiency that you could have with a power cycle is however much work you put into it, that's how much work you get out of it. I mean, that sort of makes sense in a way, but this says, no, the ceiling for efficiency is lower than that, okay? And so we're gonna be talking about calculations about how much lower and stuff like that. Okay, so let's think about efficiencies of systems. So I'm going to draw a power cycle and a refrigeration cycle. So we're going to think about the efficiency of a power cycle and a refrigeration and a heat pump cycle. The goals of refrigeration and heat pump cycles are not the same, but the functioning of them is the same. And so I'm going to sort of lump these two together. So a heat pump cycle and a refrigeration cycle are really the same thing. It's just a matter of where you put your important stuff compared to this cycle. Like if you wanted to use a refrigerator as a heat pump, you could have the refrigerator open to the outside and be sitting behind the coils behind the refrigerator, and then it's a heat pump. And if instead you want to keep your vegetables cold, you put the coils somewhere where you don't care about it, and you keep your vegetables in the other part. So it's the same thing. So first, a power cycle. Works like this. You have a hot reservoir You have your system, and then you have your cold reservoir. And heat is transferred this direction from the hot reservoir to the system, and I'm going to call that QH. And then heat is transferred from the system to the cold reservoir. I'm going to call that QC. And these directions are telling us sort of a new sign convention for thinking about this stuff. Okay, so notice that QH, positive QH means energy is going into the system. Positive QC means energy is leaving the system. And then work is produced. So that's sort of the overall functioning of a power cycle, an engine or a power plant. And the first law of thermodynamics. So since this is a cycle, we know that the change in energy is equal to 0. And so we can write this as the energy coming into the system has to be balanced by the energy leaving the system. So the first law says that QH is equal to W plus QC. And you can arrange this, just rearrange this as W is equal to QH minus QC. And now let's say we wanted to evaluate the performance of a power cycle. We'd sort of think of this as let's think of it as the utility divided by the cost. Okay, that's a reasonable way to define the performance. And so we're going to call this calculation the efficiency of a power cycle and give it the Greek letter eta. It's like a scripty N. And okay, so if we're thinking of what you get out of this, the utility over the cost. So what's the thing that you're trying to maximize in a power cycle? What are you trying to get the most of? Work, exactly. And what's the thing that you're doing in order to get work?
Producing heat.
Yeah, you're putting heat in, you're shoveling coal in there. So the efficiency is work divided by QH. And then you can substitute this in for the work and rewrite this as QH minus QC all over QH. Or in other words, 1 minus QC over QH. Okay.
That actually makes a lot of sense.
Yeah.
It's just, you put in, you get out.
Yeah. And but what's interesting here is we're still assuming everything is working perfectly. We're not considering any heat lost in places we don't want to lose heat. We're not considering any friction in the system or anything like that. And already we have a limit, even on this sort of perfect power cycle, on how much work we can get out for a certain amount of heat. You can see that, so you could have perfect efficiency if your cold reservoir is absolute 0. Well, that's not very, realistic, right?
This is like superconductors. Right?
Well, yeah, you could, but to make something a superconductor is very, very expensive, you know? And so, yeah, you're not really going to make an absolute zero thermal reservoir, you know? So barring that, if you're given the amount of, given the amount of energy that's leaving in the exhaust and the amount that's coming in at the boiler, you already have like a pretty stringent limit on what your total efficiency can be.
And that QC term, that has to do with how much heat is moving, both of those terms.
Yeah, right.
So you're saying if QC is 0, so there'd just be no energy leaving?
So
It wouldn't have any work though.
what am I saying here? So
Right, 'cause you said
Q,
if it's
yeah,
absolute
you know what?
0.
Actually, I got ahead of myself on the absolute zero thing. We're going to see that that we can turn these into Kelvin temperatures, and for like an ideal case, and then what you'll see is that perfect efficiency would come if that was at absolute zero. But we're not. I got ahead of myself because these are energies, not temperatures.
Sure.
And it'll also say that you could have perfect efficiency as the boiler temperature goes towards infinity, you know, but that also obviously isn't possible. Okay, so for now we just have this definition of efficiency, and this thing we're going to use a lot. This first law form of the cycles. Okay, so get used to thinking about it this way. Like you have the diagram of what's happening, and from that diagram you can jump to this relationship between the heats and the work. And then the refrigeration cycle, we're going to think about it the same way, but it looks a little different. This is also a heat pump. So for a refrigeration cycle or a heat pump, we still have a hot reservoir. We have our system, which is the refrigerant. And then we have the cold reservoir. And what are we trying to do here? Well, for a refrigerator, this would be the room. This cold reservoir would be where you keep your popsicles. And what we're trying to do is move heat from the system to the room, to the hot reservoir. And I'm going to call that QH. And we're trying to move heat from the cold reservoir to the refrigerant, so that's our QC. And in order to make this happen, we're doing work with a compressor. This thing is plugged into the wall and the electricity is powering a compressor. So this is the work coming in. And so we'll analyze this again using the first law. So again, this is a cycle. And so there's no change in the energy of the refrigerant over one cycle. And so the first law says, so now all the things going out, that's QH, that's the energy going out. And the stuff coming in is W plus QC. So so everything's going the opposite direction, that first law equation ends up looking the same as it did for the power cycle. And again, I'm going to rewrite this to isolate the work. So we have QH minus QC. Okay, so what's performance for a refrigerator, for a refrigeration cycle?
The amount of heat you remove per work.
Yeah, that's exactly right. So we're going to call this the coefficient of performance because it can get bigger than 1. So calling it efficiency doesn't make a ton of sense anymore. Coefficient of performance. And we're going to give that the Greek letter beta. And exactly like you said, that's perfect. So that's the heat that we remove from the popsicles, QC, divided by the electricity we need to power the compressor. And then if we substitute in our expression from the first law, we can write this as QC divided by the quantity QH minus QC.
But they still call this efficiency, like in the real world. Like this is your Energy Star.
I do not know. That's a good question.
I think colloquially,
Yeah.
at least, because I
Yeah.
looked it up. Like I have a heat pump in my garage,
Uh-huh.
and it gives you like an efficiency based on the temperature difference
Based on the temperature difference.
between inside and outside.
Yeah, huh?
So like,
Huh.
like it's only
Right.
over 100% efficient until it's
Yeah.
like
So I think
negative
I
10
think
degrees.
probably. So remember that these are not for specific. So yeah, let's look at this one, the refrigeration cycle. This isn't talking about a specific one where you've put all this effort into like, okay, how am I going to keep heat from leaving through this little gap here? Like, how am I going to insulate this? You do all these things to try to improve the efficiency of that refrigerator, right? This is just simply saying, imagine a perfect refrigeration cycle, but the only constraint is that we know this much energy is coming in here and this much is leaving here. There are no inefficiencies anywhere in it. Here's the coefficient of performance. Then you could compare that to the efficiency of your specific refrigerator. And I'm guessing that now that I think about it, I would think that that is probably what's reported as the efficiency of what you get out of this box,
Right, but this isn't like the metric, or there's no
Yeah.
like 100% efficient to compare to.
This is the thing that I would guess that you're comparing an actual physical thing to get an efficiency.
Got it.
And we'll talk about some of that stuff later on. Not too much yet. To do that, we'll have to go through the definition of entropy and some stuff like that. But okay, what if instead of this being this could still be the room, but instead of this being popsicles here, imagine this just being outside, and that would be in the case of a heat pump. So the performance of a heat pump this is also called the coefficient of performance. And we'll give this the Greek letter gamma. And how would you define performance for a heat pump?
Same thing.
Well, it's similar, except now the thing that you care about is how much, like you don't really care how much heat you have to pull from the surroundings. All you care about is how much heat you can dump into the room. And so we're going to change it from QC over W to QH over W. And then substituting in this stuff from the first law, you can write this as QH divided by the quantity QH minus QC.
Can you draw another gamma, please? I'm not. I'm just trying to figure out like because I've never done this one before. So
Oh, yeah.
I'm trying to like.
It's a backwards Y.
Is that sort of? Oh, it's sort of like why.
It's like a chromosome. Isn't that what a chromosome looks like?
Yeah. Yeah, it is.
Um, yeah. Okay. Let's see what they look like if they're typed. You know, that's why Hulk is the way he is. Gamma rays, gamma radiation.
Yeah. Yeah, I've never seen that before.
Sometimes it feels like that's like the biggest hurdle I've had to go over so far.
Is Greek letters?
Learning the new alphabet.
Yeah, you know.
The old alphabet, I guess.
Yeah, right. The old alphabet. Yeah, if you take some time knowing your Greek letters, and people will always think you're smarter than you are.
Thank you.
Yeah. So what we're going to, so these measures of performance allow us to put stringent limits on thermodynamic cycles. So something reasonable, like realistic, to compare our real world devices to. Okay. So in order to evaluate real world cycles, we need to define irreversibility. No, don't write that yet. We need to define reversibility. And so reversibility is like overall, you have a system that's reversible. Irreversibilities are talking about the inefficient elements in a device that are keeping it from being reversible. Okay, so irreversibilities. So this is like perfect efficiency, let's say. Irreversibilities are things that cost energy. So friction is a good example of that. Okay, so if you have no, so going back to the skier going down the hill, you know, you didn't talk about it this way in physics 1, but that is a reversible system if there is no friction in the, no friction between the skis and the snow. Okay, so what that says is the skier could start at the top, ski down, get up to a certain speed, and then turn around and use that speed to go right back up to the top, okay? And the system has been reversed. You haven't changed anything about the surroundings or anything. So that's a reversible process, okay? Irreversibilities, now if you add friction, the skier skis down the hill, gets to some speed at the bottom, goes around in his little loop, and there's also some friction there, and the skier gets some little bit up the hill, but not all the way to the top before all that energy is used up. Okay, so we're talking about things like that. Just keep thinking irreversibilities are like thermodynamic versions of friction, and friction is one of them, but there's other ones.
And that's momentum. So like if the momentum was the same, it's reversible.
That is kinetic energy, which is a lot like momentum. But
I get what you're saying.
yeah. Okay, so let's think about. So first, let's define a reversible system. Erase that, a reversible process is one where the system and the surroundings could both be returned to the starting state. Okay, so let's think about that in terms of the skier on the hill. So if the skier is on a frictionless hill, this skier can go down, ski around in a little loop, go back up the hill and make it exactly the top. And the skier has returned to the original position and the surroundings haven't been affected in any way. So both of those have returned to their original state, okay? Now let's think about the case with friction. Okay, so say there's a ton of friction. The skier skis down, doesn't even try to turn around, just stops or whatever. And but now the skier uses the tow rope or whatever to go back up the hill, and the skier has gotten back to the top of the hill. So the skier has returned to the starting state.
With the input of work.
Right, exactly. But the problem is that the surroundings have had to provide work by, presumably using, energy from a power plant that has changed the surroundings are no longer at their starting state. And so that's why one of those is a reversible process and one of them is not. Irreversibilities.
And even if the skier was the one walking back up the hill, you're still changing the surroundings.
Yeah, that's right. Well, then you're either using chemical energy that's stored in the skier, or the skier is eating a sandwich as he goes and you're changing the surroundings, Yeah.
And he's probably a lot less efficient than a tow rope.
Yeah, that's true. Yes, that is true. Have I mentioned this before? Anyone have any idea how much, like in joules, how much energy you consume in a day? Like, so let's say 2,000. I think this is 2,000 calories. It's about 8 million joules.
Wow.
Yeah, it's a lot.
We're great.
Yeah, imagine if we were bigger.
Okay, so irreversibilities.
I don't know what a whale consumes.
Oh, that would be insane.
Dang. But it's got the buoyancy factor.
Yeah, it's true.
Ah, dang.
I'll bet it's a lot less. Oh, but they need to. Yeah, they probably need a lot to keep their body warm. I don't know. Let's look into that. But irreversibilities are all the things that prevent a process from being reversible. So let me just give you this short list. There's 7 things here. Let me just get this in your notes. So these are, I think if you remember these 7 things, it pretty much covers all our bases for this class. Friction or air resistance. Electric current through a resistance. Inelastic deformation. So what is it that makes a deformation elastic?
It returns to the same.
Yeah, exactly. When you remove the force, it returns to its starting state. So if you have a perfectly elastic thing, like a spring is pretty close to perfectly elastic, you can deform it. That's not an irreversibility, because when you remove that force, you get that energy back that you put into it. But it does lose a little bit of energy. Everything loses a little bit of energy. This is a big one. Heat transfer through a finite temperature difference. Well, every temperature difference is finite. I mean, every actual cycle we're going to use has heat transfer, bless you, through a finite temperature difference. So that's pretty unavoidable. But in order to have a perfectly reversible process, heat would have to be transferred through like an infinitesimal temperature, difference, which would take infinitely long. So, 5th is unrestrained expansion of a gas. The way to avoid this is to have gas expand in a piston cylinder system and keep it always in equilibrium as it expands. 6, chemical reactions. And then last is mixing materials in different phases. Okay, so those are the 7 things to keep an eye out for. And a lot of what we're going to be doing coming up is just trying to figure out how to determine, like, where are there inefficiencies in this system? How bad are they numerically? Is there any way we could correct it? That kind of thing. Anybody have any questions about this? Okay, that's all for now.